Good morning, everyone. On this snow day, I decided there were a couple of questions that I wanted to talk about on the midterm because these were questions that at least 2/3 of the people seem to have answered incorrectly. So I wanted to just briefly cover some of these things and what I was looking for in terms of an answer on the exam. So the first one, and this is the one that most people seem to have missed, was how many amino acids are encoded by one and only one codon? 1, 2, 3, 4, or 5. What I was looking for was number 2 because I was really asking about how many amino acids, and maybe it should have been better about different amino acids coded by one and only one codon, because if you look at the genetic code, there are 2 codons that are the ones which only have one. First, there's the AUG start codon, which encodes for methionine. And secondly is the UGG codon, which encodes for tryptophan. It's also a little bit easier to see down here. AUG for methionine and UUG for tryptophan. And so these are the amino acids for which there is one codon and only one codon. And maybe the confusion here was codons, which are the 3 nucleotides which then encode any given amino acid. Also, bear in mind that there are a number of amino acids for which there are multiple codons, particularly arginine and leucine, that there are 6 codons for. The same thing is true for serine, and 4 codons for a number of amino acids, including glycine and a few other ones. So that was that question. The next question was ATPase activity and translation is required for confirming initiator tRNA start codon base pairing, confirming A site tRNA start codon base pairing, ribosomal translocation, dissociation of the ribosome, or RNA helicase activity. And I was looking for RNA helicase activity, and the reasoning behind that is if you look at translational initiation in eukaryotic cells, you have translocation that takes place. And translocation is once you've associated the large and the small subunit of the ribosome together with all these initiation factors, it binds onto the 5' end of your messenger RNA, and then it translocates along to the actual start codon. And this requires ATP-driven RNA helicases. And so that's the activity of, in fact, EIF4A, which is this ATP-driven RNA helicase. All of the other things on there, which were interactions of the initiator tRNA with the start codon, that's controlled by GTP. The interactions of the elongation, this is the A site of the ribosome, that's driven by GTP hydrolysis. Translocation of the ribosome down here is driven by GTP hydrolysis. And in bacterial ribosomes, dissociation is also driven by GTP hydrolysis. But when I was putting this together, I noticed that for eukaryotic translation and dissociation of the ribosome, it turns out you need ATP hydrolysis as well to get dissociation of the ribosome. Now, what that means is, in fact, there are really 2 correct answers to this question: dissociation of the ribosome, which requires ATPase activity, and RNA helicase activity. And since so many of you picked up your scantrons already, I'm going to have to give everyone an extra point because I miswrote this question. So everyone gets an extra point on the exam. Good thing that I put this together. The next question that I wanted to talk about had to do with antibiotics. This is that many antibiotics take advantage of bacterial and eukaryotic blank being different. Those being messenger RNAs, tRNAs, ribosomal RNAs, translation initiation proteins, and translation elongation proteins. The real key here is that the ribosome is really ribosomal RNAs. And so what I was looking for here is based on the slide I talked about for antibiotics. Tetracycline blocks binding of amino acyl tRNA. Streptomycin blocks translation initiation of chain elongation and miscoding while the ribosome is functioning. Blocks peptidyltransferase, ribosomal function. Binds the exit channel, ribosomal function. Purimycin, polypeptide chains, elongation, cyclohexamide, translocation reaction, acetylmycin, peptidyltransferase. So all of these are interacting with the ribosome, and the ribosome is almost completely made up of ribosomal RNAs. Last question I wanted to talk about had to do with not translation, but replication. Here, primers for DNA polymerization have to be RNA instead of DNA because they have to have a 3'OH, they have to have a 2'OH. RNA polymerases do not need primers. They are lower fidelity and they must be removed. Well, RNA and DNA both have 3'OHs, so that's not a difference between RNA and DNA. Clearly, the difference between RNA and DNA is that RNA has a 2'OH, but that has nothing to do with DNA polymerization. That the primers are lower fidelity doesn't really make a difference in terms of DNA polymerization. It would be nice if they were higher fidelity, but if anything, then you should have DNA primers rather than RNA primers. And that they must be removed. If anything, that's inefficient, and so it would be better to have DNA primers rather than RNA primers. But the big problem, all DNA polymerases have to extend from a 3'OH. How do they get a 3'OH? They get it from an RNA polymerase. And that's shown in this slide here. Again, this is just exactly one of the slides from the lectures. DNA primases are RNA polymerases. And they're RNA polymerases because RNA polymerases, unlike DNA polymerases, can start from scratch. They don't have to have a 3'OH to extend to. So that's all that I have in terms of discussion of those midterm questions that a number of people seem to have missed or we had different opinions on. There will be one more point granted to everyone that may or may not be reflected immediately in D2L, but I will add it in my grade sheet. And I hope you're enjoying the snow and not getting too frustrated with it. I will hopefully be seeing all of you on Monday.